So, okay, everybody. Good morning. Yes, good morning. Thanks for coming again for the third class. Just a comment on slides. People have been asking me or writing me emails asking to send the slides. I did send the slides, so they should. If you haven't received, please check if your name is on the distribution list of the conference. It's supposed to have been forwarded to all of you. And I cannot send it myself. I don't have the credentials to access the internet, as I said on the first day. I still don't. Okay, not a complaint. Now, third day. And today, the course on restoration connectives is going to give you some break into very abstract stuff, and give you some semantics, some modal semantics, and multi-valued semantics to deal with these kind of systems. And also there's a bonus, a hidden bonus, which is at the end, I'm going to generalize the theory of restoration beyond the unary case, beyond the case of negation. So please stay awake until the end. You might not regret. I hope. Now, just to recall, as you know, this is going to be on the test at the end. To recall the things from the last.
Is compatible with impossible which permits its deduction.
Você na página visual lá. O que você está falando que não é definido? É o K? É o Isso. Existe o
Recapture principle and the Recapture principle. Some false formulas or some denied formulas should be asserted as soon as you put a negation in front of them. Some, not all. If you do this to all, then you have a classic life. But that would seem like minimal conditions on anything you might want to call a negation. I'm making we refer to myself, but maybe you come and join. And I also introduced the notion of power consistency, power completeness. I'm going to focus on power consistency here so I don't have to repeat all the definitions. And it was the idea that you have non-dadaistic readings for formula and its negation. And consistency connective was supposed to restore what has been lost, namely the explosion principle, if you want. So making that dark triangle and the definition of power consistency become white again, make the triangle white again. And the idea was to add an extra thing, the gentle form of explosions, which tells you that, well, you might have P and not P together. You might want to read that not as a smile, but not if you add the extra assumption of consistency of P. And not to have this trivial, I add this coherence condition, say that, well, the problem is not having two of those three formulas, the problem is having the three of them together. And the standard version is supposed to be the converse to the other one. If you think that the first thing over there, gentle explosion, tells you that if you assert P and not P, you should not also assert consistency of P. Here, the standard conditions say that if you deny P, then you should assert consistency of P. If you deny not P, you should assert. That's the converse to what we have before. So it's a stronger form of consistency. And the nullify was defined as a gently explosive, power consistent logic. I realize that this doesn't get this far, but I'll have to leave this so that we solve this exercise so that we can go on. So I want to build a square, and that thing I put over there with an A inside, you recognize as a form of gentle explosion, if that circle is a circle with a smile inside. Now you can help me produce the square. Start looking at the contradictory version of it. So we're going to move this guy to the other side. Produce a classical negation of it. So let's leave these two guys here and move this to the other side. And just call it now E. Oh, that's the corner in the square. O of E. Now, what else can we do that's so easy? Oh, it's easy to dualize. You can just move everything to the other side. And in this case, we have P, not P, and I of P. And you can also do the contradictory to that, moving that I to the other side. An I for an I. Now there's something wrong here, which is I'm not dualizing the other things. Well, this guy moved to the other side, so actually now it's the dual of it, which is in here. And that's the negation of it, so it's also obviously the dual that's in there. So what do I mean by that? Well, the dual, you know, is the frown. And what about the rest? Well, if I have chosen to put consistency in that corner, and it's devilish decision, then what are the other guys going to be? Well, just to complete the square, the other guys are going to be here. The circle with a frown inside, which I'm going to write, and I can't follow things like this. And the other guys down here are the black versions of those guys. So this guy here, O, is the black version of my devilish connective. So it's the inconsistency connective. And this guy over here is the black version of this connective. Right? So you all know how to do this. Exercise. Go from the gentle explosion into the coherence conditions, the standard conditions, and do the same thing. Moving things from one side to the other and finding the conditions about inconsistency, determinateness, which is a white circle with a frown inside, and undeterminateness, which is a black circle with a frown inside, if I can manage to put it inside. Oh, down there. Okay, so all this has been covered yesterday. I will assume that it's not too hard to remember because you can just look. Sometimes we're going to have to do all the stuff very similar to this. And I have promised yesterday that I'm going to show situations in which this square is a real square and other ones in which it's actually collapses into a line. Now, there is a body of literature ever growing in which people have been talking about normality, classicality, recovery, adjustment, operators, which are interpretations of the connectives. There are some actually special volumes that have been published on this. And you have noticed, of course, that I haven't used any of those names, but I'm still talking about restoration connectives. But the point here is that we had an ideal, might not be shared and might not have been chosen by us, of perfection given by the classical negation, and we are defeating it, we're throwing it away. So that's terminology, Evandro is going to be able to confirm, it's a medieval terminology, the perfectio, and talking about the set of all, the beings which have all the perfections. This is very common at that time, and when you talk about that, this ideal, like in physics, you talk about perfect body, perfect spherical body, like you talk about this all the time. You want to restore that perfection when it's lost. And that was the aim of introducing the connectives of restoration. Now, if instead of talking about assertions and denials, I just would do the flattening that I said could be done in the Tarskian case, in the T consequence, S consequence case, and talk about the truth and the falsity. So one might read the line which defines gentle explosion as saying something about the truth, saying that if for a certain bivaluation, that bivaluation satisfies or makes true both the formula and its negation, then the third guy must be false. The consistency must be false. And when we're talking about the standard version, as I said, we have the converse. You can now see we have the converse here. It's an if and only if. Now, this is perfectly useless as a way of understanding what's going on. And no one understands logic better when they see this bivaluations. But it's very useful in the sense that you can apply it into finding better semantics, more down to earth, more explaining kinds of semantics for these systems, such as, for instance, multi-valued or modal semantics, which I chose because they're appealing, they're easy, and I'm going to illustrate in this first 2/3 of the talk. Questions? All following me? Yes.
Sorry,
The
I
exercise.
know it's from the last class, but I still don't get what are the rules for forming the square. I mean, when do you put things on the other side?
Yeah, they're implicit, right? I didn't write them down. But the idea, as you see, when you move from here to here, something is changing places. Namely, the argument rather than the operation. When you move from here to here, the operation is changing places. And when you go here, you do both things at once. That's why everything changes places. So moving the arguments is the internal negation, internal form of opposition. Here is the external one. And duality means doing both things.
And what about the negation? You have to change it.
Yes, because down here, everything is dualized.
Okay.
And that here is the same thing that we have down there. Right? In the diagonals, we're talking about the same thing. We're just changing places for the operator.
I know that's a matter of historical tradition, but wouldn't it make sense to put the dual on the diagonal?
Yes, it could. It would make sense, yes.
Yeah.
It would. So, just trying to recover the historical, not so historical tradition, because history doesn't talk about duality. But A-E-I-O was the historical thing I wanted to recover. Thanks for the question. Other questions? If not, you really probably want to see modal semantics. At least one person wants to see it. That was easier. Okay. Now there are a couple of papers on this, but I'll make it very simple. The basic idea for the para-consistent side would be that a formula, negated formula, is true at the world X of a model M in a Kripke model if there is some world accessible to it in which it's false. So it's possibly false. Okay? Now, if you take that as a primitive thing, then you can immediately, pay attention, using only classical implication and the para-consistent negation, nothing else, define a classical negation, box, diamond, the para-complete negation, consistency connective, inconsistency, determinateness, undeterminateness, with a minimal language containing only implication and para-consistent negation. So it will follow later on that every normal modal logic can be expressed in the language containing these two connectives, and only them. The other ones may be defined. What about conjunction and disjunction? You already know how to do it using classical negation and implication. Don't need to write it now. Okay? Now, the trick doesn't work for any other combination. It doesn't work in particular if you take implication and the para-complete negation or implication and the consistency connective. It doesn't. It has to be the para-consistent negation to do that. Oh, but I want to do it with a para-complete negation. Okay, use co-implication and then you can do it. Okay? Now, it has been a dream of modal logicians, as you have seen, to talk about boxes and diamonds. And what I'm claiming here is that actually they have been talking about a para-consistent negation all along, and boxes and diamonds are just definable from that. So this is what modal logic is about. It's about para-consistent negation. That's inverting history, right? Okay, yes. Rereading the past. Now, what's important to point out, of course, I claim that you can prove it using these kind of models, that the negation that I defined as square negation is classic-like, the smile is para consistent, and depending on the logic, it might be also para complete. And the frown is para complete, it might also be para consistent. And by the way, with this consistency connected, this defines an LFI, and dually for the LFUs. Okay, good. So let me write down this for exercise also. Oh, I can write it here. You see a form of De Morgan rule there as an axiom? I'm gonna write it like this. Oh, sorry. As you have seen, I just introduced a new symbol over there, which is this one. It's gonna be defined as the Q that I used yesterday. So Q is Q. And you know how to write Q, right? It's really simple. Q, U, E, U, E. It's really simple. Yes. So here I'm taking this as, yes.
Go back to the previous slide, please.
I could, yes. So, I assume it's this one. Is that all right? Yeah? Okay. So now what I'm doing is that actually I'm axiomatizing the minimal normal model logic in a language containing implication and para consistent negation, but no boxes or diamonds. In that language, you have something which looks a little bit like axiom K, and it's going to behave like that in semantically. And you have a form of contraposition, global form of contraposition. And you have a principle saying that if something is a theorem, the negation of it is anti-theorem. Okay? Now, if you don't like your logic K, you just move to your preferred set of frames. For instance, you move to your favorite set of reflexive frames, and you can express what it means to be reflexive using this form of disjunctive, or this form of excluded middle for the para consistent negation. Quite interesting that this would capture the property of being reflexive. And the property of being symmetric is captured by double negation elimination, or back negation. Well, you can also do other things, like say that there is a partial form of explosion when a formula has the shape of a para consistent negation. So if you put an extra negation, the two together are gonna explode. And this is what characterizes being Euclideanity. And transitivity involves also the similar thing, partial explosion, but now with a frown. Density can also be captured, confluence, being confluent, being serial means that the para complete negation implies a para consistent negation. Not always the case. I know you might want it. I know you might want the para complete negation to be stronger than the classical negation, and that one to be stronger than the para consistent negation. So there's something in the middle. But there's no guarantee in general, but seriality will help. If you have seriality, then you obtain your dreams of saying that the para complete negation is stronger than the para consistent negation. And if you want to have the other direction, you just assume that your frames have accessibility relations which are partial functions. Okay, of course, if you have seriality and partial functionality, you have total functions. Now, yes.
The goal condition in order by sanity.
No, they don't. No, they don't. They're very different. One is the possibility of falsity, and the other one is the necessity of falsity. So the para complete negation, it will just like intuitionistic like negation says that in every world in the future, this is going to be false. Not some world, every world. Okay, so it's box knot. And the para consistent negation is a diamond knot. I'm going to do square with this, but just want to show the simplest way of doing it, which is not the one I like the most, but I did it on using axioms. This is going to appear again and again. I'm going to show actually sequent systems to do this, which is much more well behaved. Yes.
I don't understand. So this is the accessibility relation that is reflexive symmetry.
Yeah.
Depending on construction.
That's right.
But you said that we only have implication and para consistent negation.
And then I proved that you could define, whenever you have an implication of para consistent negation, all these other connectives here.
Yeah, okay. I have the other connectives, but
You have them, so you can use them. Also
Yes, but-
conjunction disjunctions.
But the accessibility relation, the
Perfect.
axioms are
Perfect. So if you take the set of all frames, then this is a sound and complete axiomatization. If you want to axiomatize the set of all reflexive frames, you add that extra axiom, and so on.
So, until you add, say, PKT, power consistent negation is also power complete.
Though it's no longer power complete after you add, which is the
Yeah.
same thing you said.
Yes.
Yes, that's right. So that's why I said it could be both power consistent and power complete. So in PK, it is both power consistent and power complete. All right, definite. It's clear?
no.
Ask
Look
again,
it up.
ask again, ask again.
Yeah, I really don't understand. You just said cryptic, and I'm supposed to know why.
Yes, yes, you're supposed to know. That's right. Yes.
Okay, I don't.
Okay. But is there another causal model logic here? Maybe not, but I'm assuming that
Yeah, fair enough.
it's a structure having a non-empty set of worlds and an accessibility relation, and I'm using it since the beginning here, writing this. Okay, so that's the satisfaction condition for the power consistent negation as primitive in the language.
Okay, so there is the set of words,
Yeah.
and the okay.
So if you're an intuitionist, you would prefer to have something like this. For every world, you have.
Yeah, no, it's that they're very dense slides. I started reading the bottom part here, focusing on that, and I didn't notice that. Okay, sorry, apologize.
There was a click in which this was alone, but
Yeah,
it
I
was
know.
flashed.
Yes.
Okay, now, this is gonna improve. I just wanted to show that actually you can capture in this language a lot of interesting properties of classes of frames in a very appealing way. Now, I need to discuss what's the theory behind this. So again, you're gonna see all this thumbs up and down, and you're gonna see that we start with this ideal classical case in which unary connectives actually have only two possible values, the true and the false. Now, in that case, there is obviously just four kinds of connectives which you can define in classical logic, unary connectives. The first one, it's like it produces tops. The last one produces bottoms. And the ones in the middle are well known. This one here with a minus has a name, it's called negation. And this one, this poor guy here with a symbol plus, is not often referred to. People will assume it's transparently there, but it's affirmation. All right, now any normal model will satisfy this property. It follows from normality, it's weaker than normality. It's the congruentiality, if two things are logically equivalent, then you can replace one by the other inside any context. Now, what I wanted to mention is that there are also extra things you might want to require. Of course, if you have any one of these two lines, you have that one. Right? This is stronger. If you have, just a moment, if you have that B following from A is enough to conclude that this connective is monotonic with respect to that notion of consequence, then you can use it twice to obtain congruentiality. And the same for this form of contraposition. You can use it twice as soon as you know that this connective is antitonic with respect to that order. You can use it twice to get congruentiality. Yes?
Just to be clear, the hash is any unary.
Yes, any of those four. Okay, in fact, when I write this sentence is true for all the four. When I write this first one here called preservation of consequence, then it's not true about negation, but it's true about the other three. And when I write this form of contraposition here, the reversal of consequence, then it is true for three of those guys. Again, it's just not true for affirmation, but it's true for bottom, top, like connective, and it's true for delegation connective. Okay? I want to separate what it means to be positive and what it means to be negative. Because I mentioned to you that there is things like a box with a plus inside, in the first talk, a box with a minus inside, and so on, and I want to really define them in abstract terms. Now, one thing that we can already guarantee, which is super easy, is that there are some very nice interactions in between preservation of consequence, and some form of distribution of plus over conjunction and or over disjunction. And similarly for the reversal. This is super easy, so we should be able to do it. So let's try to prove DM 1.1. So it's one form of De Morgan using what we have here. So what do we want? There is a disjunction on the left, so let's start it with the other side. Now, most people will be willing to concede that disjunction introduction is acceptable, but you can actually prove it from the basic rules of a standard disjunction. I'm assuming that you already had did this exercise in the first talk, and now what I'm going to do is just use reversal to produce this. Okay, now I changed this number symbol for the paraconsistent negation. Why did I do it? Because that's where it might appear. But is that really the case? Let me just put it straight way. Actually, it's going to be wrong. So let me put it in a neutral way. That's right. Some negation here. Oh, maybe I use a symbol for negation then. It's negation, right? You can recognize this if I write this. Now, you can do the same thing for not psi on the right, and you can use the conjunction to get what we have here on the last line, DM 1.1. Okay, exercise, just finish that derivation. Very simple, so you always have it. As soon as your connective is antitonic, is reversal, with respect to the consequence relation, you're going to be able to prove DM 1.1 and also DM 2.1. Of course, it refers to conjunction in this case. Okay? Great. So this has nothing to do with what I wrote in here because it's another form of De Morgan. So where is it? Well, let's see. Let's explain what boxes and diamonds are. So what is a box? A box, don't tell anyone after you leave this room. A box is a weak form of affirmation. Oh no, modal logic actually goes much beyond classical logic. It does affirmation and more. It's a fragment of classical logic in which you have a form of affirmation which is weaker than the classical. Okay, here. Now, as you have seen, we already have these two things, always. And I wrote the other two. What do I mean by them? Well, if your connective respects PM 1.2 plus, I'm going to call it a box. It behaves like a box. And it's a positive box. On the other hand, if it respects PM 2.2 plus, it's a diamond. And it's a positive diamond. Okay, you might not have intuitions about this, though you might be doing modal logic your whole life. But I'm going to add a little bit more. Say that if you put a box plus in front of top, you also have a top. It's also a theorem. So box of a theorem is a theorem. And if you put it on the other side, box in front of a bottom is an anti-theorem. Okay, now you notice that I'm using the language of distributive lattices, bounded distributive lattices now, with bottoms and tops. Okay, now, while you might not have intuition about this, I claim that most of you have intuitions about negation. And I'm going to present you two kinds of negation, the box minus and the diamond minus. Again, we had this in the last slide. I'm going to add one of these two guys. If I add the guy on the left, I'm going to say that I have a box minus, just like negation in intuitionistic logic. If I have these other form, then I have a diamond minus, which is the reading that we have for the paraconsistent negation. It's possibly false. Okay, so I just defined what it means for a modality, a unary modality, to be called positive or negative with respect to the behavior that it displays in an environment containing conjunction, disjunction, bottoms, and tops. So with respect to bottom, the negation of a bottom should be a theorem. And with respect to top, the negation of a top should be an anti-theorem. But this only works if the negation here is a box minus, like an intuitionistic logic, part-complete logic, or if the negation here is a diamond minus, like in part-consistent logic. Okay, so you've seen the things on the left before. I wrote before that square of oppositions will be on the left-hand side, the positive modalities, and now you know what I was referring to. And on the right-hand side, the negative modalities, and you also know now what I was referring to. But if you don't like to use those symbols, you can go back to your simple boxes and diamonds without pluses. And on the other side, use your frown and smile to do the negative versions of those modalities. Okay, and they are related by the usual operations that we have seen before, usual notions of opposition we have seen before. And box dual to diamond, frown is dual to smile, and you have all the other relations over there. Yes?
Is the affirmation the tool of negation?
Yes.
So why the positive square is equal to the diamond? But positive square is equal to the
Because there are two kinds of affirmations, just like there are two kinds of negation.
Okay.
And one of them is dual to the other.
Oh.
Just like when you define classical negation, it's self-dual.
Mm-hmm.
But if you break it in two parts, if you only talk about if A is true, then not A is false, you have one side of this duality which is dualized into if A is false, then not A is true. So I'm breaking it in two parts. When you have all of them together, then you have the classical affirmation. When something is at once a box and a diamond, positive box and positive diamond, it's classical affirmation. So when you have all the PM rules in here, you have classical affirmation. And when you have all the DM rules in here, so all of the Morgan rules, you have classical negation. More questions?
Yes. That's the first part. Because I understand the second part. The Morgan rules are applied.
Here? Yes.
The negation of the first part, it doesn't apply to the subjective piece too. I don't understand.
I'm not sure I understood the question. Let me see. Do you agree that these forms of the Morgan pretty much represents all forms of the Morgan?
Yeah, I think that the bottom part I can understand because it's the Morgan. Right?
All of them are.
The first part I don't understand why it's not the Morgan.
It is, but the first part is for free. What's in green here is for free. You have it for any connective which is a reversal connective. You have it for free. What you don't have for free is the second part. And I'm telling you that if you can make choices with respect to the second part. If you want to add one of them, then you have a certain kind of negation. And if you want to add the other, then you have another kind of negation. And if you want to have both, then you have classical negation. You see? In this environment, right? Of course, there are para-consistent logics which have all of the Morgan rules. That's not the point here. This is a modal version in which you usually don't, and usually you don't identify boxes and diamonds. But you might, if your collection of frames is a total function, you will identify boxes and diamonds. Okay? Yes?
Yeah, I don't quite get what's the role of the table in the previous slide.
I wanted to break. Let's look at this. If you look at all of them at once, these will be characteristic of affirmation. It's just a plus in classical logic. And I'm breaking it into parts and saying, well, there are two kinds of pluses. There is a plus which have only 3 of those 4 things, and there's another plus which has only 3 of those things, but not the same.
But what is the true and false there? Because we're in a Kripke frame.
There's none. Just use that as a motivation, right?
Okay, so it's just
Yes. No, there's not. This is purely abstract. There's no true and falsity there.
Okay.
Now, the idea was that, and that's why I was trying to convince you that boxes and diamonds are weak forms of affirmation, because a full form of affirmation would have all the rules. Okay? Why, when you have this, you don't have all of them. And when you have that, you don't have all of them. So you have less. So it's a subclassical logic. Modal logic is subclassical, not super classical in this approach. Actually, most non-classical logics are super. If you choose the right signature to work with. Here I would have to start with a signature in which boxes were present from the beginning and they represented affirmation. And then I'm going to take some things out. Or diamond was affirmation. Then I take some things out. Take some rules out, and it's no longer an affirmation, it's a box or diamond. Okay? Other questions? Similar for negation, yes.
I want to ask you because when you say just split down, then you can restore the class. But how do you recover the class?
You have to add a little bit more, but you recover over distributive lattices the behavior of a classical conjunction with respect to the complement, and similar for the classical disjunction. But for full classical logic, you have to add a little bit more. You notice that I made my life a little bit harder by not having implication anywhere here? This is going to be important. It's going to be really important, because as you saw at the beginning, just by having an implication like a power consistent negation, you have everything else. It's too easy. I don't like games which are too easy. Why play rock, scissors, paper when you can play with Spock and the lizard, right? Okay. Thanks. Now, I wanted to just display the possibility of having deductive systems for these logics. So here I put some form of labeled tableaus, and here another form of tableaus like the ones you find in Hughes and Creswell. And you can use this to prove this formula here. Let's do it. So I want to start in a world, let's call it 0, and use it as a label. And here I'm going to have this, but not have that. That's what tableaus look like, right? You try to refute. So I'm going to have a minus here. It's like in the book of Grande, non-classical logics. And that's where we start. Now, what do we have here? We have a minus in front of a disjunction. Classically, this is going to amount to both having a minus in front of them, right? Yeah. Both parts. So 0 in front of. Oh, I'm using the wrong Q here. Sorry.
No problem.
And I go into the wrong Q's.
The right side of the
What? Where's consequence? Here. Yes, sorry. You've been laughing at me, right? Yeah, but this one is much better, of course, because B, P, P, Q are all produced by rotations. It's so much better. Yeah. So what can we do here now? So we have these two things that came from here. I like to add things to the usual tableaus because I want to know where things come from. So from some rule of disjunction, this comes. What else can we do? Look at the two rules we have there. We have a rule for minus in front of a smile. And we have also not used this thing here. It's a plus in front of a smile. How do you prefer to start? Maybe I start here. Because there's no bifurcation, right? I can start anywhere I want. So I just add here 0 R, say 1. And then I write that this is the place where this is witnessed. So here I'm going to have this, right? So this came from here by the rule on the left there on system 1. Well, easily I can go from here using conjunction into these two guys. Q, right? And the other guy, the rule on the right over there, tells you that whenever you have this, and you have one of these two guys, you can conclude something about world 1. In this world, because I have this guy and this guy, I can write this. Right? Something wrong here. It's a bifurcation, right? It's a bifurcation. So here are two possibilities. That's minus, it was too easy. Okay. Now these two guys together.
Which field is this?
Awful. Awful. So here we have this. So I just divided by 0. And here I have this, and that's over again. Okay, if I were to present you a tableau system, you would love it. That's how it looks like, with relational formulas, with labels, and so on. But you might not be a big fan of this kind of thing. You might want all kinds of systems. I'm not exercise. Do the same for system 2. Okay, now let's go into other systems in which you don't have to enrich the language by adding relational formulas, in which you don't have to add labels, in which some people say you make no confusion in between semantics and proof theory by adding these labels which look like you're talking about the true and the false. This is how it looks, it's just labels, all syntax. But anyway. And it's more modular, so you can add rules for the other systems and nice properties. So let's go to sequence systems. And as I said, I'm not going to use implication because that makes life too easy. Too easy. Okay, here it is. A sequence system for the logic PK. You know most of the rules here. You know identity cut, weakening on both sides. You know how bottom, top, conjunction, and disjunction behave like. But you might be curious about how consistency behaves like, and you see that there is a rule for adding a consistency sentence on the left, right? No one, and another one to add it on the right. So very classic like this is a system which is a standard form of consistency connective. If you don't want it to be standard, you throw away one of those two. Exercise, find out, well, which one? It's the second. Okay, the one on the right. Too easy exercise. I like that one. You have also rules for the undeterminate connective, which is the dual to consistency. Not the determinate, it's the undeterminate. Okay, and what about negation here? Oh, that's just biased. There's just one side. Remember that you have to throw away in non-classical logic part of what was classical. So you cannot move things freely from one side to the other. In the paraconsistent case, you can move things from right to left under certain conditions. So there's something happening also with the context. And here, the similar thing, the dual thing for the paraconsistent negation. Now, some people will say, I don't like this kind of rule so much because you mess with the context. It's not going to be analytical. It's going to be a terrible system to work with. It's not. It's great. I'm going to show you. We proved lots of great things about it. For instance, very easy to show that this sequence system is sounding complete with respect to the, say, expected class, because you have to do some little adjustments. The class of all frames with very few adjustments, and enjoys cut admissibility, so it's a cut-free system. And it's analytic in the sense that you can produce your derivations looking at a generalized version of subformulas, in the sense that circle is more complex than the thing that's inside the circle. It's just to make life a little bit easier, but then you can prove that you can implement a theorem prover for this system easily. Now you can do for the many of the other systems too, but this is really hard because it's not given to you that you can prove cut admissibility for all those systems. You have to do case by case. Okay, for the PK, it's simple. I'm just going to give you some other ones which also work. Yes.
Yes. What was the technique that you use to prove the cut elimination theorem?
Semantics. We use non-deterministic semantics based on the PhD work of Odi Lahab. So there is a very interesting idea, which is to each sequence rule, we associate two kinds of constraints. One constraint is dictated by the main connective, and the other constraint is dictated by whatever you're doing with the context. So everywhere else but in these two rules, you don't have to do much because the contexts are kept. But in these two rules, The induced condition by this thing we do with the context gives you the full meaning of negation in the system. Okay, so it's a very nice, I do recommend having a look at the technique, which is fantastic and gave us the possibility
You
of doing
need
that.
this technique because of this rule.
Yes.
The connectiveness with the content.
Yes, yes. That's why we use this theory that actually sequence are not what most people think they are. Sequence are based on two things. There are two kinds of rules in parallel. Rules that apply to the main connective and rules that apply to the context. That's a brilliant idea by Codiglano. Okay. Now, similar reasonings will give you these other rules, which might look surprising if you just look at them without thinking much. And you see that some interesting things you get like explosion for the para-complete negation or excluded middle for the para-consistent negation as soon as your frames are reflexive, and similarly for symmetric frames, stereo frames, total functional frames. And so on. Now, rather than showing the next result, which I find to be really interesting, I think it would be useful to try and convince you that this system actually allows you to prove that formula or that sequence over there. Let's do it too in this system. So let's start as everybody should start from the root. Let's put it down so we have space.
But what would it mean to prove or to reject a method to remove the system?
Which method? No, it was the object language version of the principle using negation, right? It's not the version I presented in the first lesson, which was the version referring to consequence. That's the negation version of the principle, the one that people actually like. They say, oh, principle of no contradiction has to do with negation, doesn't it? Yeah, that's that version.
So that's consequence relation.
That's normal. That's usual
That
one.
you prove the one and prove
Yes.
the negation of the
You
other.
have all the rules, the usual rules for that one. I'm just replacing here for a sequent so that we can work on the system. And easily you know that we can use the rule for disjunction on the right. To change this for a comma. So that's disjunction on the right. What can you do now? New rule. New rule is purple. Yeah. It has a smile, right? So the one that allows you to push the smile into the left. Now what's the delta here?
Empty.
Empty. What's the gamma? The set containing P and Q. Right? So here we have P, Q, arrow, P, Q. You can continue from that, right? Conjunction, introduction, weakening on the left, on the right, identity, over. Okay. It's analytics, so actually if you didn't know how to do it, you could just use the prover to do it. Yes?
The system allows the explosion.
Well, it depends on which explosion you're talking about, right? Here you see that PKT allows for explosion for the frown, but not for the smile. The smile is a para-consistent negation. Now the system PK allows for no kind of explosion, either for one or for the other. It's very, very weak. The para-consistent and the para-complete negation are para-definite. They're both para-consistent and para-complete.
There is a third one. I see the second.
What's the third one? Here?
Yeah. Third, left, there's uncertainty.
Sorry, can you give the name of the rule? It's arrow what?
Bottom on the left.
Bottom left, here.
No, bottom on the left.
Bottom on the left, yes. Yes. What about it?
I think it's
What? Sorry?
I read it as the uncertainty.
It's saying that you can add absurdity. It is an action, right? It's an action of the system. You could replace it by a rule saying that if you have gamma arrow delta, then you have gamma comma bottom arrow delta. But actually you don't need, because bottom gives you everything, so you can just introduce as an axiom for whatever gammas and deltas you want. It saves you time.
Because when I see the natural reduction over what implies everything.
Here, this.
Anyway, you mean it is not.
Yeah. Now, and that's no longer pk, right? It's pkt on the first line, pkb on the second. The first line, you can push a conjunction here in this comma and a disjunction here in this comma. Right? Okay. Other questions? I'm not going to do proofs for those systems, but if you want to check the paper in which it's developed, actually, they have improved and also be sound complete, to have the cut free and nice, analytic also. Now, what's really interesting is that we managed to prove something that we really wanted with these systems also, not only see usual rules of negation inside this system, but also see that some of these systems allow you to define classical negation and some do not. For instance, you can define classical negation in PKT even if you throw away these two connectors. Doing this with the other two connectors. Similarly, for the other signature over here, similarly for the system with seriality or functionality. Now, what is really nice is to prove that classical negation is not definable in a lot of systems here. And the way we prove that is using the cut-free formulation of the system. So these sequence systems are really useful for proving that classical negation is not definable. For instance, in PK, or PK with symmetry, PKT without any restoration connective, and so on. Questions? That's the final slide on modal logic. Yes?
Yeah. So a couple of questions on this frame definability. So all of the properties you mentioned are basically defined also in modal logic. There are something that is stronger, meaning like irreflexivity is not definable in the standard modal logic. Can we do it?
No. You cannot do more. You cannot do more. Actually, you can do less because I threw implication out.
Yeah. And do we have some correspondence theory for?
Yes. You can develop the same kind of theory you have in the other case, but if you have implication, it's the same correspondence theory, right? The one without implication, yeah, it's more interesting, this one actually, because it puts a limitation on what you can express. Other good question? Yes.
Can you give me intuitive understanding about internal, how it's called, the Brown related to the semantics? Because you define it, you go back to the slides.
Yeah, but I won't go back. If it's just an intuitive idea you want, the smile says that it's possibly false, and the frown says that it's necessarily false.
Yeah, I just wanted to relate it to the semantics.
Yeah.
So you can give me an intuitive understanding why it's defined.
Why is intuitive understanding on?
In the relation to the semantics.
This?
Exactly.
I'm not sure what you're asking because, oh, sorry, pushing to the wrong side. Because I wrote this clause here, and here I wrote the dual clause, and that's the whole intuition that I can give you. Because this one talks about a diamond, a box minus, and that one is a diamond minus. So the power consistent negation is a diamond minus, and the power complete negation is a box minus.
I think
Necessarily false, possibly false.
Okay, I think I have a very similar question.
Oh,
so
yes.
maybe I don't
Yes,
know.
please.
So like for example, in other logics, for example, like the intuitionist logic, so we have a very good like what model corresponds to the critical semantics represents like it is like as like a cognition status of like an ideal mathematician, right?
Right.
So it may be helpful if we have like such.
I'm not going into an epistemic reading of this, and in intuitionistic logic, the only thing you have which is not in here is that you have the heredity condition. Okay? You might think of a bad heredity condition for the power consistent case, and then you do have a dual intuitionistic logic. If that's what you want. But then you also want to change your implication for co-implication and so on. Actually, Grande has done that. Yes?
I was thinking if this generalization for modal logic is valid for all kinds of modal logic. Because if you try to translate elliptic modal logic to geometric modal logic, for example,
yes,
you can arise some paradoxes. So I was thinking if there is some attempt to develop some kind of similar system for.
Yeah, that's a very good question. I mean, every normal modal logic can be recovered here already on this first slide. But you might want to have some more interesting modal logic, such as temporal logics, for instance, which you have fixed point operators. How are they going to be expressed using this kind of language? This I think would be interesting questions which no one has worked on. Yes.
Yeah, because for example, one paradox.
Yeah.
Geometric logic is the contrary to the paradox.
Yeah.
And you can find it by introducing the disjunction, and you have a different correlation for.
Yeah. You would have to rewrite the paradox in the new language to see if it gives you some insight on what's going on, and I think it might. Yes. I push it as a problem we could be working with. Really nice. Yes. Other questions before going to many valued case?
Can you extend it to substructural logics as well?
Oh yeah, throw in some of the structural rules here.
Okay.
Okay, things get harder. These results are not guaranteed. And so the full answer to your question is that it hasn't been done. Let's do it. Okay, so I just gave you something which is a tool, and there's a lot of things you could do with it, and it's so easy because you just have to allow for a little change in the initial propositional signature, and your motivations are going to be about negation and lots of new things might. Okay, so I'm going to flash many valued semantics if I want to get to the end, but there's a couple of examples here which are interesting and you might have seen before. An obvious idea to get a negation which is not classical is put more truth values in there and use them to express inconsistency or undeterminedness. So this idea has been explored, for instance, in the logic P1, I1. As you see, the output of the truth tables is fully classical, just T and F. The B and the N disappear. And I take B to be both, so a designated value, and T to be true, if you want. And this logic it behaves power consistently and power completely only at the atomic level. Okay, another logic which is four-valued, very well known, Campinas four-valued logic, which is also para-definite, because you see that N goes to N and B goes to B. So this is a designated value whose negation is designated. This is undesignated, the negation is undesignated. So para consistent here, para complete here. Okay, now they don't have restoration connectives and we want to add them, of course. It's so much nicer when you have it. Let's see what happens. First, restoration connective one might consider is this very simple one. It really looks like P1, I1 because you see what comes out of it is just T and F. So that's probably what you want. You want to say that, well, these guys here are non-classical, so the negation of them is false. Okay? They don't behave well. So you mark the good behavior as being the classical behavior T and F by a T and a T, and the rest is false. Now what happens here is you have a collapse of the square. Consistency coincides with determinateness. So you don't have real antonyms here, it's self-antonym. You have restoration, but only the basic form, not the standard form. And I'm not going to show you, but you can define a classic-like negation, which is basically throws F and N into T and B and T into F. Behaves classically. Okay, you can define using this. The language of P1 I1 or the language of FDE plus any one of these two connectives. Now, more interestingly, there's another option which is also available for FDE, which I prefer, which is the one in this column here, in which actually you throw N into P and P into N. And when you have the conjunction of two of these guys, like P and N, in the lattice. And you have the conjunction of B and N. In this direction, you're going into F. Right? And when you have the disjunction of B and N in that direction, the direction of truth, you go into T. So you have the behavior here marked by these two guys, throwing them to the right place. So now there's, I even put a classical negation here because it doesn't really matter. You take FDE, you add this classical opposition, notion of opposition to FDE, or you add any one of those four connectives. Any choice you pick is going to allow you to define all the others. So what is the consistency connective here? Or it's anything that you can define when you add a classical negation, or vice versa. Now, note that here it's very clear to see that the classical negation of the consistency is not equivalent to the para-definite negation, the original negation of FDE. So beware of this confusion. Don't assume that inconsistency is the negation without telling me which negation you're using. So I remember that I always have this one in mind when I'm talking about the contradictory version. Another thing which might be interesting is that the consistency of a formula is equivalent to the consistency of the negation of the formula, or a definite negation of the formula. There's a lot of collapse. This system is more interesting than the previous one because you have four connectives which are different, but you might have just one of them and define all the others from it. Okay? Now, you might not like this. You say, oh, you remember that everything became easy with a classical implication. It also becomes too easy with a classical negation around. Let's do it without. We did it in modal logic. We can do it here too. Another way of turning FDE into an LFI is, Martin, you have worked on this.
Yes.
So, add more structure. So instead of having four values, add extra values. Define your consequence by way of degree preservation. And I put this very small so that you don't try and bother to read, but just look at the guy here, which is fully classical, the consistency determinateness, which coincides. It gives you only T's and F's. The idea is that, well, do whatever Dunn-Delno tells you to do in this inner bilattice here. Extend by adding another guy here and another guy here. So make the connectives behave like they behaved before, and tell me what happens if you consider a new value here. Okay? And when you consider a new value there, something really interesting happens. First of all, what I'm doing here is not just for the case of the four bilattice, but it can be done for any De Morgan algebra. You can axiomatize the class of the new algebras here with this new symbol that we call perfect para-definite algebras, with adding some magical axioms and equations, right? Magical equations here because we're doing an algebraic approach. And this is a term equivalent to the class, very famous and important and respectable and nice and loved class of involutive Thom algebra. But on the right language, instead of having that novel that no one understands what it means, it has a consistency connective, which is the thing that we love. Now, interestingly, in this logic, which is 6-valued, no classical negation is definable, and we can use the semantics here, the algebraic interpretations to prove it. Yes?
Could you find an intuition behind this null operator?
No, it could never, ever, ever. I'm gonna die before that. Ask Italy if she had an intuition about the null in her logic too. Possibility operator. Let's call it like this. It's not. It's not even a diamond minus. How could it be a possibility operator?
And you think that 6 is the minor amount of elements that you need?
Yes.
In order
to do this. Yes. Yes. I think you proved it for your formulation in the other language, right? And yes, we can prove it also here. When you do the shorter version, then you will be able to define class negation. You're going to have degenerate example of this. So the circles will no longer be significant. Now, we do have an LFI, an LFU, and we can prove a derivability adjustment theorem, which is the same as in the logic C1. You just have to add consistency on top of the atomic sentences to be able to recover any classical reasoning. Nice. So you can also do without classical negation here. Yes.
In which way this logic is connected with the logic associated to stone involutive algebras? Involutive stone.
Well, it's adjustment of the language, right? It's term definable there and vice versa.
Yes, but you have many ways to associate a logic to an algebra. 6 is a logic that preserves degrees of truth with respect to this class, and you could have another. Another
Yes. So I cannot say much. It's still degree preserving with respect to this new class.
Coincides.
Yes. Because we can produce from one algebra, from the class of involutive stone algebras, one algebra in the class of PP algebras and vice versa.
And of course, you are citing.
Yes, of course. And what's interesting is that we showed that you don't do much more than this, actually. And we can go back and forth. If that's really into very tight connections. We can produce one algebra from the other. When we come back to the same algebra we started with. So in the sense, that's the best sense I can say, they're the same, right? Same up to an adjustment of the language. Now, if you want to do this to any other logic, you pick the logic which you have with a certain set of connectives, and we showed how there is an algorithmic way to add a number of different rules about consistency or determinateness, about the restoration connective, which will give you a sound and complete axiomatization for that logic. So I just showed the simplest example, and this actually works for any other logic in the class. And here there's some verification of things. These are the things I showed on the first day, the set Hilbert systems. And you see that these commas here are verified here when you use the rules 3, 6, and 6. You have here a P, which is one of the things you might want. Here you have a not P, another thing you might want. And here you have the negation of the restoration connective, which is the other thing. So once you have one of these alternatives in any branch, then you have proven the set of alternatives. While here you have not proved it because I have two alternatives here and this is not there. Okay? Again, this is analytic, these are very interesting properties, has actually been implemented in a theorem prover, and you might want to use this file from us for free. Okay, this was at the end of the last slide. I'm gonna jump. Two-dimensional things, crazy. Okay. Just wanted to show this, and I need a couple of minutes to talk about this. If you want, I can return to the other. Now, this is the bonus part of the talk, because we did so much of a theory about restoration connectives that you might say, oh, well, how did you pick all those choices? Where do they come from? And I claim that there is a way of actually looking at your goal or your truth tables and producing a theory of restoration, whatever is the connective you work about. And let me start with a very general theory and an example which is not a negation at all, a binary connective. So I claim that all that we did here goes beyond negation. This course was actually not a course about negation, but there's so much to talk about negation that it occupied all the time until the last 10 minutes. Now, suppose that you have a binary connective. I don't care what you do in these places here, but suppose that you're not very, well, you didn't make up your mind about what you're going to do when both inputs are false. For instance, you might have implication. The classical logician thinks that implication should be true here. The intuitionistic logician doesn't really agree with that. So, well, depends. So maybe this is a dispute, a medieval dispute between the classical and the intuitionistic logician. They start to argue with each other and say, oh, we have two options. Now, the classical logician says, okay, I want to enforce this cell here to be such that if both inputs are false, if I connect them, it should be true. Because he has classical implication in his mind. Now, how can we help this guy do what he wants? Well, we can write this goal saying that, well, if P and Q are both denied, then this guy cannot be denied. You see, this was what we wanted to do. Now, suppose we don't have it, and we want to recover it. Well, at least let's concede that there is some possibility that this will happen. The possibility of denying P and Q while asserting this. So that's what I put in red here. The classical logician doesn't want this to be a possibility. He wants this to be the case. But let's allow him to have that possibility. I'm going to call this a condition of legitimacy for his connective. See, you saw that word legitimacy there somewhere? Similar. Now, if I want to work on the A corner, then I just say, I'm going to add something which, whenever it appears here, it allows me to recover what the classical logician wanted. You see? That's in here. You don't have it in general. That's my goal. But if you can assert this about P and Q, then you have it. Very similar what the consistency connective does. Okay, now we can imagine that we're transporting this through the diagonal and pushing this guy to the other side. It becomes a node. We can also produce other two guys and put them somewhere. But the other two guys in the other diagonal talk about the dual connective to that, which is not a condition on FF, it's a condition on TT. Okay? The dual goes to the other side. Let me put all this together. We still have, using the four things which are in this square, in this slide, a square. As we did in the last lesson, a square that uses not the connectives themselves, but rule by rule. I produce a rule from another rule. Remember, there was rule of conjunction introduction. I dualize it into disjunction elimination. I produce the antonym of it, which is the condition on NOR. I produce the contradictory to it, which is the condition on the NAND. Okay, here it's condition on two different things. Now, you say there's something missing because in the case of consistency, you also have those coherence conditions over there, saying that, look, you want to recover that goal there of putting that one of these three guys had not to be denied, right? You can't deny them all at once. But you don't want this to be the case with only two of those guys. So I'm taking all the possibilities here. So if it's just P and Q, not good. If it's just P and P sharp Q, not good. If it's just P number Q, if it's Q and P number Q, also not good. But if you put all of them together, yes. If you put P, Q, and P number Q, then this guy lets you recover what you have been lost. If you want standard versions, you also have exercise to put the converse conditions. The converse conditions are going to say that you cannot, it's a judgment incompatibility thing, right? You cannot deny this while asserting that. You cannot deny this while asserting that. You cannot deny this while asserting that. Okay, binary connective, very weird. You haven't seen that before. You can do with any connective you like. How does that relate to what we have done in the beginning? Well, suppose it's unary, and suppose you want to enforce this to the horror of the paraconsistent logician. You want to enforce that the negation of a true formula is false. Right, so that's the goal. P, not P, explodes. Well, the legitimacy condition associated to that is that at least you should allow for a situation in which you have P being asserted while number P is denied. So T and F. Legitimacy condition is one of the two that we had there. Falsificatio, verificatio, like in the church. That's falsificatio. That's associated to any negation. I want both actually, but the only one that's associated to what I'm doing right now is falsificatio. And I can produce the square. We did it already actually. It was the exercise at the beginning of this lesson. And you can do the other two, which was obviously the exercise that you did while I was speaking here. You do all that, right? This is the consistency connective with the coherence conditions on the A corner, and that's the standard version of it on the A corner. It's just a particular case of a more general theory that applies to any connector. You can restore what has been lost. If you have a problem, go and solve it. If you have a problem with incompatibility, you're not afraid, you're not sure what you're going to do, go and solve it. You have a problem with your disjunction, you don't know if it's inclusive or exclusive. There are two ways of deciding the problem, right? Depends on your goal. There's one thing to restore if you're talking about inclusive disjunction, another thing to restore if it's exclusive. If you want to restore several things at once, just put them all together modularly. I hope you're going to find this useful. Thank you very much. I can even go back to things I didn't present, and I can answer questions about any part of these slides or previous slides. Yes. That's it, you.
Yeah, so then it's not impossible for me to ask a question because I thought I had the same opposite that it's impossible. Because every time I want to ask a question, somebody's like, oh, I don't have question or something like it. You don't see me. So.
I see you.
Yeah, I see you. Oh, okay, so for sure.
Avatar.
Yeah, thank you for the talk. My question is just like, I was just wondering, I was just wanted to ask, like, regarding the PK.
Yes.
Like, since I noticed that at some point you grammar and Lógica,
could you speak, could you stand up, please, because we are not understanding what you're saying.
I am. I see you, I hear you.
I didn't know I would understand how I would fix my hair better.
Oh.
So I was just, I wanted to ask, like, regarding this PKC consistencies, I understood that you were referencing Lógica and I think there are a lot in natural deduction.
Yes.
So I was just wondering whether, are there any, like, can these kind of consistencies be a great model with categories? Like,
Oh.
I'm just wondering, I don't know, because, you know, like, there's a theory versus intuitionistic logic, and you model groups in these kinds. I mean, whenever there is natural deduction persistence, I'm asking myself, like, can this be model? I'm not sure. I'm just
So you're asking whether I can model the phenomena here using category theory?
Model, like, could you model groups inside these kind of systems as arrows in categories? Like, I was wondering, because in categories we get these equalities of groups.
Yes.
We have equalities of arrows and we can interpret them as equalities of groups.
Yeah.
So I'm just like wondering, can we also talk about, I mean, why couldn't it be about the qualities of groups in these kind of systems and whether categories could be the right ground to do this?
I love the idea. That's what I say. Is category the theory the place to do this because it's so easy to think about the opposite category, for instance, and dualize these arrows. Yeah. 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 Yeah, I think using the intuitions from the square, this would be a very appealing thing to do. So let's do it. Yeah, so there's a lot to do. There's a lot to do, and I think you have very good idea. They didn't mention anything at all, thanks. There is some work on positive, negative modalities in the literature. There's a lot of work on positive modalities, very much less on negative modalities. And people like Vakarelov, Selani, have worked on this, and mostly through algebraic approaches. So they haven't favored so much the categorical approach, and I think it's very sound, nice idea to do it. It hasn't been done. Thank you. Your colleague.
Yeah. So my question is like regarding the last section, when you generalize to
yes, to any
binary connected. I was wondering from the start of your courses actually that you assume classical implication and study the varieties of implication.
Yeah.
Would you instead start with the varieties of implication and assuming that's communication and recover the theory?
Yeah. Oh, so there is some work in this direction actually, using intuitionistic implication. So generalizing this a little bit further with implication, but for implicative lattices, or with directly with implication as the residuum of certain conjunction. Then I think it's more interesting in that case because whenever you put classical implication, things become too easy. So if you're saying that it would be interesting to look at implicative structures, I would suggest that this is done in a larger environment. Like this also has been proposed to be done with swap semantics, twist algebras, and there you don't need to commit to a classical implication, so you can add something weaker. And then there will be a large variety of things that will come out of this, which will be non-classic or normal modal logics on top of non-classical logic and things like this. It's a lot to explore there. Thank you. Yes, get on the back first.
I was thinking about when you think that modal logics are sublogics of classical logic.
Yeah.
And so is that proof of that there's some connection with the post-completeness?
No, there's some connection with you know, when we have first order logic and you prove that it's equiconsistent with propositional logic, you produce a mapping in which you just forget all the quantifiers, and then you have a fragment of propositional logic, everything is in there. It's the same thing here. You can forget all the boxes and diamonds, and everything that you have in modal logic is propositional. Now, you're not supposed to forget and believe that you have what you had before, because actually you had a weaker thing than you had before, right? So you're not going to have everything. You're going to have part of what you had before, because boxes and diamonds don't have everything that an affirmation connective would have. And a similar thing can be done for negation. Instead of forgetting, you add a negation in place of it. So you go back to idea number 1 on the previous slide that I had, and then you show that it's sub-classical in another sense.
Okay.
Yeah, you raise your hand first. Yes.
The system may not have
Stand up, please.
And speak up to. Speak up to.
I don't see
It doesn't have an implication, yes. Is this a question?
Yeah. It is, it can be defined or.
When you have a classical negation around, then it can. Right? But I purposefully left the implication out because I wanted to consider fragments in which classical negation was not definable. So for this logics here, you can define a classical implication. Now, as I showed in the beginning, if you had that classical implication from the start, you would not be able to say that classical negation is not definable. It will be.
Because it is not a definable.
I'm sorry, say it again.
Because it is not a definable.
Because it's not definable? Yes, I wanted to study in which conditions it is definable. I'm saying that the problem is about classical negation, but the problem could be about classical implication. Under which conditions can I define classical implication inside a normal logic written in this language?
So the other or system.
Yeah, the ones here on the top will have an implication, the ones here on the bottom will not. Because if you cannot define a classical negation and you still have a bottom around, then you would be able to define a classical negation from the implication and the bottom. That's why I had to throw it out.
But you may have a weaker implication.
Yes, that's related to the question that somebody asked before. And I answered at least related to that, saying that you might have an intuitionistic implication, it's the residuum on a certain class of algebras. You might have a weaker implication, and then it's going to become really interesting. And some people have worked on this. Again, Bakarelov has worked on this. Other people have. Selani, I think, also.
And sometimes you may have an implication for which modus ponens doesn't work.
Is that an implication? Can I restore the perfection that you just lost? Is modus ponens? Yes, I can.
Yes.
Yes, I can, yes. But as soon as it doesn't respect modus ponens, also have the right to question its status as an implication, because it won't have a legitimacy condition for being an implication, which is given by the ideal perfect classical logic. Yes?
So I want to understand the scope of recovery. Where does that theory apply? If you go back
Yeah.
to the last place.
I didn't give a general theory, I gave an illustration of a theory, right? So the idea is you start with any two-valued connective.
N-value?
But for to do the n-valued case, you have to do an extra trick. You have to make a collapse into the bivalent semantics. Here, I'm introducing non-deterministic semantics, two-valued non-deterministic semantics, and trying to determinize it, not by way of adding axioms, but by way of adding a new connective which filters out the models that I don't want to have. So that's the scope, the idea that instead of recovering by adding axioms that's going to say to you that, well, this must not be the case, so this is the case, you recover by adding a new connective that plays the role of a companion to the connective that you have in there. So the companion of that connective is this one here, and it lets you recover the meaning, the deterministic meaning of the connective.
Okay, so my question is actually, first of all, well, you have a goal property that you want that connective to have, and you create a recovery. From that goal, I guess you can induce the legitimacy conditions, the definition of
everything.
Okay.
And the goal is bivalent, remember, because every S-consequence relation is bivalent. So it's important that I start with two, right? The goal says something about assertions and denials.
Sure. So I cannot have a goal, for example, something which talks about syntax. I don't know, something about relevance of implication.
Oh, no, not here.
Okay.
But you can have all the stuff.
Can you have a goal with a black triangle? For example, I want to recover para-consistency or something like that.
Not here.
Okay.
Sorry.
You can only recover properties which can be stated with white triangle.
In terms of rules of a certain two-valued non-deterministic connective, yes. Of any arity. But one thing that you might have, which is quite interesting, and I should mention, everything we had at the beginning of this talk, you might want to associate to any recovery connective model semantics and a multi-valued semantics. And I know how to do it. I'm working on it. Okay, so advertise, this can be done. And it's really fun because it's very appealing, easy to do, and as you saw, it can give you lots of things that we had before. And then there is a whole bunch of things that you might want to do after that, which is not on the abstract level, but on the proof theoretical level, or in some other interesting level of logic, and prove general results and take them to some other framework. So this is just the tip of the iceberg. It was not what the course was about, but I hope it was a good bonus. Thank you very much, everybody.